Let's look at some more examples of multiplying fractions. When we first introduced this, we used smaller numbers, and that makes things easier to see, but sometimes using smaller numbers makes the problem so easy it's hard to see the broader strategy. So here's a problem where we might have some strategy to have to deal with. One approach, the traditional approach, is to associate the dilation with the dilation, 14/39 times 13/35. I'm going to associate the 14 and 13. 14 times 13. 3 times 4 is 12. 3 plus 1 is 4. 182. And then associate 39 with 35. Right? Well, 39 times 35. Definitely not getting that in my head. 5 times 9 is 45. 15 is 9. 3 times 9, 27. 9, 10, 11. 1265. Wait, okay, that's one problem with writing so small. Say 5 plus 0 is 5. 9 plus 7 is 16. 1 plus 1 plus 1, there's a 3. 1365. Okay, maybe some of you caught that first mistake. Okay, 182 over 1365 is not my answer, because I now have to reduce this fraction. What does it mean to reduce a fraction? It means identifying from our previous problems these common factors, right? If I just multiply straight across, 2 times 5 is 10, 3 times 6 is 18, that's easy. Now I have to recognize 10 is a multiple of 2, 18 is a multiple of 2. Well, I'm basically here anyways, right? I'm doing 2 times 5 to get 10, only to turn around and break up 10 as 2 times 5. I'm doing 3 times 6 to get 18, only to rewrite 18 as a product of two different factors. Well, it's a lot easier to write 6 as a product of two factors than to split this one up and maybe have more to cancel, right? When we have these giant numbers, I'm supposed to look at 1365 and not only know what might go into this evenly, but what might go into this evenly and 182 evenly. Yikes. Right? Well, 182, that's an even number. Well, 1365 isn't even. There's not going to be a 2 here that I can cancel. So even getting that 2 doesn't get me very far unless something over here cancels with something down here, right? I'm not just looking for factors, I'm looking for common factors. And maybe the only way to do that, if I didn't already have this, if I started here and asked you to reduce, the only way to do that is to factor. I need to know the factors of 91. That's kind of hard. Factor this, ends in a 5, so I know it's 5 times something. Then split this up. Once I have the prime factorizations of both numbers, I can cancel all their common prime factors, right? You don't have to just factor out the GCF all in one fell swoop. Sometimes factoring completely means you can factor each common factor pair as it appears. But I don't have to do any of that. I already have it factored to begin with. Where did 182 come from? It came from 14 times 13. So let's stick with this 14 times 13. Forget about this. 14, I know how to factor that. That's super easy. I know my times table is at least this far. 13, I recognize that as a prime number, right? The only way to multiply to get 13 is 1 times 13. 39, maybe some of you don't have that recognized, um, but 3 plus 9 is 12. 3 goes into 12 evenly, so 3 must go into 39 evenly. 3 goes into 3 one time. 3 goes into 9 three times. As long division goes, that's about as easy as it gets. 39 is 3 times 13. It's an ugly 3 times 13. 35, that ends in a 5. That's 5 times 5, 10, 15, 20, 25, 30, 35. Okay, 5 times 7. If you don't have it memorized, it makes it a little bit harder. Doesn't mean it's impossible, but having these times tables memorized is really useful. Right. Now I can look for the multiplicative identity hiding in plain sight. Okay. Remember, this means 2 times 7 times 13 times 1/3 times 1/13 times 1/5 times 1/7. I'm not going to write it out this way. It takes up a lot of space and people get intimidated. But I really have 8 factors here. Well, 13 times its reciprocal is 1. 13 thirteenths is 1. Do you see the other one there? 7 sevenths is 1. And 1 times 2 is 2. 1 times 2 is still 2. I have 2 times 1 times 1 times a third times a fifth. 3 times 5 is 15. 2 fifteenths. Right? That's how we're going to do this problem. If we multiply, get these giant numbers, maybe that first step of factoring is easy, maybe even that is difficult. Once I have the 2, maybe we recognize 91 as 7 times 13. Maybe we don't, and we have to try a bunch of long division until we stumble upon 91 divided by 7 is 13. 1365, well, that's 5 times, have to do the long division there. Then we break that number up. Eventually we'll get 5 times 3 and 13 and 7. But this, yuck. We want to use the factoring that's already given to us, cancel, get our nice simplified number. This is fully simplified. We've performed all possible operations. We've divided by 7. We've divided by 13. We did not divide by 3 because 2 doesn't divide evenly by 3. So we just leave that divided by 3, that divided by 5. We leave those there, and that's our answer. Now we can look at a similar problem. Keep it as 14/39ths. But then instead of multiplying by 13, let's use another 14. And instead of 35, let's use 37. All right? What can we do here? Well, it turns out nothing. But we don't know that unless we first try. 14, that's 2 times 7. 14, that's 2 times 7. 39, that's 3 times 13. 37, it's not even. It doesn't end in a 5. 7 plus 3 is 10, so it's not a multiple of 3. Let's see, 2, 3, 5, 7. It's not a multiple of 7. 35 is a multiple of 7, and that's only 2 more. 3, 5, 7, 11. It's not a multiple of 11. Not a multiple of 13. 39 is a multiple of 13. And we've pretty much exhausted all of the prime factors that could go in without going over the top. Right? So it turns out 37 is a prime number. Well, here's our problem. 2 doesn't cancel here. 7 doesn't cancel here. 3 doesn't cancel up here. 13 and 37 don't show up there. Nothing cancels, so the only way to simplify is to carry out the multiplications. 14 times 14. Oops, forgot my 1 there. If you don't have it memorized, you can actually work that out. 4 times 4 is 16. 4 plus 1 is 5. 1 times 4 is 4. 1 times 1 is 1. 5 plus 4 is 9, and there's the 1. Right? 56 plus 140, 196. Or you could have done 2 times 2 is 4. 7 times 7 is 49. 49 times 4, 9 times 4 is 36. 16, 17, 18, 19. Right? It's the same 4 factors being multiplied. It's just a matter of how we associate them. We're still going to get 196. Down here, 39 times 37. I'll just do it that one way. 7 times 9 is 63. 21 plus 6 is 27. 3 times 9 is also 27. 3 times 3 is 9, 10, 11. 7 and 7 is 14. 1, 2, 3, 4. 14, 43. Now, this might not seem like it's worth a lot, but it really is a huge benefit. Once I've multiplied, I can rest assured that this is my answer. I don't have to stare at this, racking my brain, trying to figure out what could go into both of these numbers. Maybe 2. No, this is odd. Maybe 7. I don't know. Does 7 go into this big number? I don't have to waste time. I know I'm done. I can move on to the next problem. When I look at 182 over 1365, that doesn't look any more likely to reduce than 196 over 1443. I've got a pair of big numbers. They don't have an easy common factor like 2 or 5. But this one doesn't reduce, and I know that because I tried. This one does reduce. I know that because I didn't just try. I skipped this completely. I factored fairly easily, canceled, and I'm done. This process is hard. Sometimes that's the only thing we can do because we're starting with the big fraction. But if we're starting with it already as a pair, already partially factored, that's so much nicer. Right? Reducing, multiplying, it's really the same process. It's just, are we starting with it partially factored or are we starting with the big numbers? Now with signs, that's the same thing as with whole numbers. There's a negative, so there's a negative. If they're both negative, the opposite of a negative is positive. Right? Signs with fractions work exactly the same way they do with whole number inputs, with integers. Right? So we don't have to remember a whole new set of rules with signed fractions. We remember how multiplication works with fractions. We remember how multiplying by -1 twice or 3 times or only 1 time, how that works, and we're good.